It is a great pleasure for me to welcome you here at Moscow State University.
We're really pleased that you made it here. We had several people that he was very close with.
Maybe 20 core collapses per second in our universe up to redshift 2, and maybe 60 to the particle horizon.
It's important to point out that due to so high density and also if we have very high magnetic fields, extremely high magnetic fields.
In their simulation, they solved the Einstein equation. As a result of core collapse, black hole is.
The interaction effect depends on the outer layers of ejector, which collides with the surface.
Is evolving, and also the major merger rate, and the change is dramatic from redshift 1.8 to 0.
Spectral lag. It seems to me spectral lag is the last but not least property which scientific community started to investigate in prompt emission. So now I will speak about prompt emission. Afterglows of galaxies.
There is another source of afterglows. It's afterglows from the heated gas. If you consider only the gamma ray flux, then if it's surrounded by the
accretion was converted to the outflow, the jet, the relativistic jet. It starts to interact with the surrounding medium. It sends a strong shock wave into the surrounding medium, which transfers energy of the jet. The surrounding medium is heated up to very large temperature, and that in turn produces gamma rays via synchrotron process.
We test this correlation between the Lorentz factor that we measure for this sample of burst and the isotropic energy of the prompt emission, the isotropic luminosity, and the peak energy of the prompt spectrum.
Quite simple spectrum, power law or maybe power law with some break. The range we are interested in. So let's say from the redshift of 10 up to maybe 20. First stars start to appear.
Now, is there science beyond gamma ray bursts in this energy range? Just to remind you that, of course,
which show the spectra of energy deposits in both insulators from gamma quanta.
By looking at this distribution in real data, we can get the polarization property. In particular, we can get 180 degrees. It's a peak period.
then I mainly want to talk a little bit about afterglow light curves and spectra or spectral energy distributions, and give you my view on whether the afterglow observations better conform to theory or not with respect to the problem.
It's quite important to understand the mechanism of particle acceleration, because in
When you're talking about instruments in the MeV range, you use words like terrible, unlucky, very difficult, and crazy, okay, because of this background problem, and you don't get the advantage of pair telescopes. I'm going to require less than 15 arc-minute location for these bursts, okay, because I want to go follow them up with an optical or other telescope, and I insist on a large field of view. The answer is you can stick.
We understand that if you want to see the more distant object in the universe, you do not need the large telescope. You need telescope as small diameter.
We compare the calibration sets. Now for monitoring mode we
Our experiment, which measured GIB far from the Earth, can measure gamma ray burst with such duration.